Well, let's move on to the next example. Well, the function we have is also a piecewise function when x is less than 4, defined as x squared minus 8, when x is bigger than 4, defined as x plus 4. So f of x is continuous on each piece. Right, since again on each piece it's a polynomial, right? Here is parabola, here is a line, but basically they are polynomials. The only discontinuity is at x equals 4. Right, so we check the one-side limit to figure out if the limit exists or no. And if we need to move on, then we check the function value, right? Then to make the conclusion. So one-side limit. So for x equals 4, check it from the left. Which when x is less than 4, defined as x squared minus 8, that's the function we use. So we substitute in. A little bit less than 4, but that's fine. It is put inside a polynomial, so regardless if it's a little less or a little bigger, that's still the value of 4. Right? For square minus 8, that is 16 minus 8. Is 8. From the right side, it is function defined as x plus 4 when x is bigger. Approach from the right is approach the path of along the path of x plus 4. So when we substitute in, well, we get a 4 plus 4, and that is 8. So therefore the limit of f of x as x approaches 4 equals 8. Right, that's what we find the limit. But f of x is not defined at 4. You could say it's undefined or it's not defined, that's what doesn't matter. Right, that the value is equal to 4. So f of x has a removable discontinuity at x equals 4, you could say, and continuous elsewhere. Removable discontinuity at x equals 4 and continuous elsewhere. We know it's continuous because the nature of the polynomial function. Right? The polynomial function is continuous basically. So that is what we have. So that is how we discuss the continuity. Right? If first check the limit, if limit exists, then we'll move on. If limit not exist, we say here at the given x is non-removable discontinuity. Once the limit exists, check if function defined or maybe not defined. Right? If defined is not match or not defined, we call it removable discontinuity. If function value matches with our limit, then we have a continuous at this given point. Then overall, to see, well, it is removable discontinuity and continuous elsewhere. Well, what we had seen was the continuity on open interval a to b. Here we have on closed interval a to b. Right, so which means it's just an extra 2 points. Function is continuous on the closed interval a to b if function is closed on the open interval a to b, which means every point inside a to b is continuous. That's what the definition we had before. And for the endpoints, we need to discuss about the discontinuity and the limit approaches from the right of A equals f of A. The limit when x approaches B from the left side equals f of B. That we can say a function is continuous on the closed interval a to b. Well, we don't care if we only discuss about this closed interval, right? We don't care if maybe function is has a jump or has discontinuity at the other side, or we don't care if they are attached together. But for this closed interval, exactly the function is continuous. Or do not care on other conditions, but only the closed interval, which only the one side limit need to be satisfied. That is good enough for the endpoints. Right. Everything inside should be continuous, and we should have a solid point, in other words, on the A and on the B. Right. To make a solid point, the path approaching value should equal to the function. Approaching value from the left at B should equal the function. Approaching value, which is the right side limit, approaching to A from the right, should equal the function. So that is called continuity on closed interval. the intermediate value theorem, which is the theorem you have seen in your calculus, pre-calculus, basically, in your pre-calculus you have seen. If the function is continuous on the closed interval, if function is continuous on the closed interval, it would be f of a is not equal to f of b, and the constant k is within the range of f of a to f of b. Such graph and that is our k constant. F of k is bottom, f of b is up, and for any value in between the f of k, f of a and f of b, there is a k on the y range, on the y-axis. So what the theorem say is that, well, when it's continuous, there is at least one number C inside our interval from A to B. It has to be inside because the k is not belong to A, not equal to B, so it cannot be the endpoint, right? And such that f of c equals k. Which means here we have at least one number that the y value of our c is equals to the f of k, is equal to the k. In our function here, since it's going up and down, we have, if the k is here, then we have three values. If k is this value here, then we have one value intersecting and one value of the c inside A and B, such that they are equal. Right, so that is the intermediate value theorem. Is used to test for the y value. Right, so that is what it is. You have seen the intermediate value theorem before in your pre-calculus already, I believe, right? Should be. And the basic condition is the function is continuous on the closed interval. Right, so use the intermediate value theorem to show that the polynomial function has the interval in 0 to 1. Has a 0 in the interval 0 to 1. So from the intermediate value theorem saying, well, it should be continuous on the closed interval, then f of 0 cannot equal f of 1, and if the 0 is inside our f of 0 and f of 1, the range of that, then we're good enough. Right? So a couple of things to check. First of all, f of x is a polynomial. Which is everywhere continuous. Hence f of x continuous on 0 to 1. If it's continuous everywhere, then of course, not only for open interval 0 to 1, but also for closed interval 0 to 1, it will be continuous. Right. The second thing, we check f of 0. That's 0 to the cube, plus 2 times 0 minus 1. 0 plus 0 minus 1 equal to negative 1. One cube plus 2 times 1 minus 1, that's 1 plus 2 minus 1, which is 2. So the value has a 0, which is the 0 is belong to the interval from negative 1 to 2. That's the second thing. Right? F of 0 is negative 1, f of 1 is 2. That 0 of the y value is between those two range. Right? So no matter how they look like in the middle, but the 0 is negative 1, the 1 is 2 here. So maybe only one value, maybe more than one value in between. But that's at least one value since function is continuous. That should be past the x-axis in some way, right, since it's continuous. So together by the intermediate value theorem, there is at least one c between 0 to 1 that f of c should equal to 0. In other words, the c is the 0 of f of x. Right? That, in other words, that at least one 0 in between this interval. Right, that should be at least one. So that is what we have, the intermediate value theorem. The theorem itself is simple, but we need to check and explain the condition out. Later you will see some other mean value theorem or some other theorem that the condition itself are the keys, are more important than what we have later. The thing later is just to find it equals to 0, but first thing we need to show is use the theorem to show it exists. Right, so that was everything about the one-side limit and continuity of a function. And we move on to the next section of section 2.5, the infinite limit. Such thing we have seen was like before the limit x approaches to 0 from the left of 1 over x. We have said that we could substitute a value that is very, very small to get a very, very large number. And when it's getting smaller, this number will be getting also the value getting larger, which is the value is getting smaller, so approach to negative infinity. In other words, that is a constant divided by a 0, which the 0 is a negative 0, that will get a negative infinity. Right? Because 1 over small number will be, extremely small number will be infinity, and we have the sign is negative here. Right? So introduction still. We have a function that f of x equals 3 over x minus 2. We can see from the picture, right, that the limit of x approaches to 2 from the left is negative infinity, and the limit as x approaches to 2 from the right side is infinity. Infinity and negative infinity just means they are unbounded, going down and going up, from to the bottom and to the top. Right? Doesn't mean the limit exists. Right? Here, the limit still not exist when we see the infinity over here. It's just showing that, well, it approaches to negative infinity and approaches to positive infinity as x approaches to 2 from the left and 2 from the right side, which graphically that is called the vertical asymptotes. Right, the vertical asymptotes. So properties for a constant C. Let's say a positive constant. As long as it's a constant, it adds with infinity, that is infinity. If subtract infinity will be negative infinity. A constant times infinity will be positive infinity. Constant times negative infinity will be negative infinity for the C to be positive. And when C is negative, that will be opposite, right? So we have a positive constant C. And C over a infinity, that equals 0. When it's over a negative infinity, it's still a 0. When C over a positive 0, that is positive infinity. When C over a negative 0, that is negative infinity. Right? That's positive 0 and negative 0 means 0 approaches from the right side or 0 approaches from the left side, which is still not 0. It is true that a constant over an exact 0 will be undefined because it's undefined. Right? It's not defined. It doesn't have an actual value when it is equal 0. But when it approaches to 0, like the value is a little bit bigger than 0, that will be on the denominator is will be very, very small, and when you flip it, that will be an infinity. Right, so when we divide a number to be extremely small number but still positive, that is infinity. When divided by a positive number by a number that is 0 approaches from the left side, which is a negative number, but still have value, absolute value to be very, very tiny, that we get a negative infinity. And of course, when c is a negative constant, that will be negative infinity, and this will be positive infinity. So a little different. Okay, so that is the property we have. So when we defined limit x approaches 2 from the left of 3 over x minus 2, what we can substitute is when we find a number is a little bit smaller than 2, well, we can draw a real number line if we want. 2, and this one is a little bit smaller than 2. Right, so if we get this 2 minus a little bit smaller than 2 minus the 2, we sure will get a 0. But this 0 is a little bit tiny, is a little bit less than 0. Then we'll get the negative infinity. Right, so still, right, if you have a little confused about what we are doing here, we know that it will become a 0 and maybe the positive or negative infinity, we're not sure. So you can use instead on your paper or wherever you want to use it, then finally we figure out it will be a negative infinity. I like what we just showed. But anyhow, right, if a number is a little bit smaller than 2 and we minus the 2, that will be a little smaller than the 0. Right, for the limit when x approaches to 1 of 1 over x minus 1 squared, to find it, we find each side one side the limit. Right? Limit of x approaches to 1 from the left side. That is 1 over a little bit smaller than 1 minus 1, which will get a little bit smaller than 0. But even though when we square it, it's still a 0. Approaches to 0 very, very tiny, but when we square it, it becomes a positive number. Equals infinity. Also one from the right side. A little bit bigger than 1, minus 1, that will be a little bit bigger than 0. But when we square it, it's still a little bit bigger than 0. It still get a positive number. Right? So we get infinity. Right, so we get, if we see it in the graph, right, the x-y axis, for 1 we get a vertical asymptote, and both of them will be a vertical asymptote approach to positive infinity. It doesn't mean the limit exists, it just means for each side it approaches to positive infinity. Right, that's what this is. Find the limit of f of x when it approaches to -2 and when it approaches to 2. Well, this function, before we can simplify it, f of x, x plus 2, x minus 4. That is x minus 4 over x minus 2 when x is not equal to -2. Right, so the -2, in other words, we can find its removable discontinuity, that when we find the limit of x approaches to -2 f of x, it should exist and we don't have to use the one-sided limit. That is -2 minus 4, -2 minus 2, which is -6 over -4. Is 3/2, right? 3/2. And for the other part, the limit at x approaches to 2. That 2 is the remains denominator, so we need to use one-side limit to see where it approaches to. F of x, or simply after we simplify. That is a number a little bit less than 4, a little bit less than 2, which still 2 minus 4 is a 2. Only care about is at 0 if what that value is, right? 2 minus 4 is -2, and a little bit less than 2 minus 2 is a little bit less than 0. Well, we know that constant over 0 should be infinity, but the sign is negative over negative, so it is a positive infinity. Right, and also on the right side, that is a little bit bigger than 2. Oh, we should put a parentheses. Right, even though a little bit bigger or a little bit less, that's still -2. Right, but the denominator is a positive 0. So we still know that a number over a number over 0 should be infinity. And what we should have is negative over positive is the sign to be negative. Therefore we get a negative infinity. Right, so it helps us not only to draw the function, we see that, well, the two to be vertical asymptote, but what we actually see is approaches from the left is positive infinity, approaches from the right of 2 is negative infinity. Alright, so left is positive infinity, approaches from the right is negative infinity. And then we'll see also the horizontal asymptote. Somewhere -2 is a hole basically, and so without the aid of extra point, we still can know the shape of the graph roughly, about what it is. So we can see the infinite approach of that. But for the first part, when x approaches to -2, we know that this one could be simplified out, then we get a limit, which is called the removable discontinuity. Another way we can check the removable discontinuity for rational function is when it can be reduced. The one being reduced out is removable discontinuity. We'll verify that by finding limit. The one it stays is non-removable discontinuity. In that case, once our limit is infinite, that is the type of infinite non-removable discontinuity. But basically that is non-removable. So that is our section 2.5, yields to infinite limit, and that is everything of our chapter 2. Right. And next time we'll go to chapter 3. The chapter 3 is all about differentiation, which is connected by the definition we see before, by the difference of quotient, and by the idea that the difference of x are going to approach to 0, then what will happen is the slope of secant line will become the slope of tangent line. Right? So we will see them in our next chapter.